Hi there. In this video, we will explore how to solve three-dimensional forward kinematics. Before that, it answers one fundamental question. If I know the rotation angles of all my robot's motors or servos, where exactly is the tip of the hand in 3D space? To calculate this, the robot uses the lengths of its rigid metal bones, or links, and the angles of its joints to map out its precise x, y, z coordinates. We will focus on a standard 3-axis robotic arm, the configuration used in almost all industrial and hobby projects. It has of 3 moving joints. The base joint, or you call the waist, rotates left and right on the floor. It controls the horizontal panning angle θ1. The shoulder joint moves the upper arm up and down. It controls the shoulder angle θ2. The elbow joint bends the forearm. It controls the elbow deflection angle θ3. The physical measurements needed. L0, height of the base pedestal, from floor to shoulder axis. L1, length of the upper arm, shoulder to elbow. L2, length of the forearm, elbow to hand. To solve a complex 3D problem easily, engineers split it into 2 simpler perspective shifts. Look from the side, 2D, flatten the arm to calculate total height, Z, and total ground reach, R. Look from the top, 3D. Spin that ground reach around the base to calculate the true x and y coordinates. Before calculating positions, we must find the absolute angle of the forearm relative to the ground, beta 3. Beta equals θ2 minus θ3. Why is that? Well, to keep things visual, draw a dashed extension line straight out from the upper arm. The elbow angle θ3 is simply how far the forearm bends away from that line. If the arm does not bend, θ3 equals 0 degrees, the forearm stays glued to the extension line. If the elbow bends downward, it actively subtracts from the shoulder's elevation. For instance, if your shoulder points straight up, θ2 equals 90 degrees, and the elbow bends down past the horizon, θ3 equals 135 degrees, the equation gives 90 degrees minus 135 degrees equals minus 45 degrees. The negative result perfectly matches the visual reality of an arm pointing downward into the ground. Next, look at the robot from the side. We use basic trigonometry, cosine for horizontal components, sine for vertical components, to find the ground radius, r, and total height, z, which is r equals L, 1 times by cosine θ2, plus L, 2 times by cosine beta, and z equals L0 plus L, 1 times by sine θ2, plus L 2 times by sine beta. You might ask why for R and Z. Let me explain. So firstly, for R, the upper arm casts a horizontal shadow on the floor equal to L 1 times by cosine, θ2. The forearm casts a shadow equal to L 2 times by cosine, beta. Adding these 2 shadows together gives you the exact total reach, R, from the central axis. Secondly, for Z, we must stack every vertical height component. We start at the pedestal height, which is L0, add how high the shoulder lifts the arm, which is L 1 times by sine, θ2, and add how much the forearm reaches upward or downward, which is L 2 times by sine beta. And remember, the L0 is not necessary if you don't have a base. In other words, you only add it into the calculation when you have a base height. Finally, look at the robot from directly above. The entire arm acts like a single line of length r spinning around the center point based on the base angle, θ1, which is x equals r times by cosine θ1 and y equals r times by sine θ1. Again, why? Because the ground radius, r, calculated in the previous step, is just a raw distance. By multiplying r by cosine θ1 and sine θ1, we break that raw distance into standard grid coordinates on the universal x and y floor map. Alright, let's go through a problem together by using our discussed equations. The first step we need to do is calculating the absolute forearm angle beta, which is to find the absolute orientation angle of the forearm relative to the horizontal plane. That is, beta equals θ 2 minus θ3, which is beta equals 90 degrees minus 135 degrees equals negative 45 degrees. Now, why is this? That is because a negative angle shows that the forearm point downward below the horizon. Now we finish the first step. The second step is to calculate the horizontal radius, r. That is to find the total horizontal footprint or reach along the table surface, which is r equals 20 times by cosine 90 degrees plus 15 times by cosine negative 45 degrees. You will get r equals 20 times 0 plus 15 times 0.7071 equals 10.61 centimeters. Now, why again? Because the upper arm points straight up. Cosine of 90 degrees equals 0, contributing 0 horizontal reach. Only the forearm extends outward. Step 3 is to calculate the height, z, which is to find the total vertical height of the arm's tip above the table. That is z equals L0 plus L 1 times sine theta 2 plus L 2 times sine beta. If you plug the corresponding value, you will get z equals 10 plus 20 times sine 90 degrees plus 15 times sine negative 45 degrees. Then it equals z equals 10 plus 20 times 1 plus 15 times minus 0.7071, which is 19.39 centimeters. Because we start at base height of 10 centimeters, climb straight up the upper arm of positive 20 centimeters, and descend down the forearm of negative minus 10.61 centimeters. Lastly, we need to convert to 3D space, x and y. Now, if you look at the top view to examine the base, you can see a rotation angle theta, 1 equals 30 degrees. Use our next formula equation, we get x equals r times. Cosine theta 1 equals 10.61 times cosine 30 degrees equals 10.61 times 0.8660 equals 9.19 centimeters. For y, we get y equals r times sine theta. 1 equals 10.61 times, sine 30 degrees equals 10.61 times 0.5000 equals 5.31 centimeters. Why is this? Because this projects your flat horizontal radius, r, onto the 3D ground floor grid based on the direction the robot faces. So from our answers, we get the final coordinates. If you combine them, you will get 9.19, 5.31, 19.39. And done. Hope that's simple to solve. To wrap up this tutorial, it is crucial to understand that real-world hardware requires one final vital step before these equations work. If you are building any hobbyist or complex robotics, you know it is servo calibration. That is the angles used in our calculations. Theta 1, theta 2, theta 3 are absolute geometric angles, but your microcontroller only speaks in raw PWM signals or raw encoder ticks. To bridge this gap, you must map the physical limits of each joint. For example, you might command a servo to its maximum position and measure with a physical protractor that it sits exactly at 90 degrees, recording that raw pulse width value as your reference baseline. By establishing these precise offsets and scaling factors in your code, you make sure that when the software requests a 90 degrees shoulder angle, the physical hardware moves perfectly to match your geometric model. So in our next video, we will take this a step further and explore how to calculate the correct coordinates in 3D forward kinematics with dynamic conditions, diving into how shifting structural loads, real-time acceleration, and physical joint limits affect your arm's precision on the fly. See you there.